Well, we're going to do lots of adventurous things with levers, but let's start really simply with a lever that we've all played on in a park before. So if we think of a seesaw, we can recreate our seesaw lever by using the card strips and a pin. The best thing to do though is take your card strip and mark it first. So what I've done is drawn a line right in the middle. So these are 2 centimetre strips. So a centimetre down, a centimetre down. I've drawn a line right down the middle. And that means we can put the pin anywhere on that line, and that makes our measurements of the motion a little bit more accurate, so we get better results for our little experiments. Then if I know what length the lever is, so I've made this, let's have a check, is it 20 centimetres long? I've made it exactly 20 centimetres long. So that might help us later as well. So measuring things is important. And then what I've done, I've said, well, if it's 20 centimetres long, let's divide it up into 5 centimetre parts. So measure the first 5 centimetre, measure the next 5, measure the next 5, and that takes us to the end. So 20 centimetres in total. There's the very centre, and we know our little cross there is the centre of the pin board. So let's pop the lever in. There it goes. And then see how much it moves. So let's start with it lined up on that centre line, the sort of dashed line as our centre line. And then we can simply, well, first of all, let's describe the lever. We'll say a lever is only a lever if this part in the middle, which has got a proper name, if the pivot is present. The pivot has to be there somewhere on the lever. And on a seesaw, right in the very centre, you've got that place where the plank of the seesaw with you on one end and your friend on the other is actually attached to something. It doesn't fall off every time you have a go at a seesaw. It's held in place, but it still lets the seesaw move. So it's held in place, but it still lets the seesaw move. The pivot makes the seesaw move the way it does. And if you wanted to describe that motion, you could quite simply say the down motion on one side causes the opposite on the other side. So now let's move it. Wait a minute. Now they swap places, don't they? Well, that's gone up and that's gone down. And that's the whole fun of a seesaw. We can play the game where you go up and down. By the way, a seesaw is an example of a lever, but where does the name seesaw come from? Why is it called a seesaw? There's a lovely little bit of research for you to do. So there's our very first lever experiment there, but not quite, because we said we were going to measure things. So let's measure. Let's take this end that goes up and say, well, how far up does it go? We can make it go as far as we want, but let's just keep it simple and within the board. Let's make it move up 1, 2, 3, 4. So anywhere on that line, if that arrow ends up on the line, let's have a look. There we go. 1, 2, 3, 4. It's moved up 4. And what about this end? That's where it started. 1, 2, 3, 4. It's moved down 4. So it isn't just a case of the simple seesaw lever moving up and down. It's the case that it's moved up 4 on one end and down exactly the same amount, 4, on the other end. And these lines are in centimetres, so my simple lever moves up 4 centimetres on the right hand side and down 4 centimetres on the left. But we know levers can do the opposite of that, because it wouldn't be a fun seesaw without it. So just as easily as one end can move down, it can move back up again. So the up and down just keeps swapping around. The important part is the pivot, and on a seesaw we have exactly the same distance on one side to the pivot as for the other side to the end and the pivot. So these distances are equal, and that's how a seesaw lever does what it does. So these distances it moves up and down are related to the distance between the centre and the end of the lever. So in other words, the movement we get, that 4 centimetres down and 4 centimetres up, ooh, that's 5, 1, 2, 3, 4, 4 centimetres up and 4 centimetres down, actually depend on the length of the lever, but not just its overall length, the distance between the centre pivot and the end. So we'll explore that in the next little exercise. By the way, if you were to draw a line and follow where it goes, look, the lever does not move in a straight line. Look at that. It's moving in anything but a straight line. It's moving in a curved path. So there's another thing we've revealed about levers. Curved path. So the path that the lever moves through is actually a curve. There it goes. I suppose if we continue that all the way around, the curve would become a shape we all know, which of course is a circle. So levers can move in a curved path, but they can make things go up and down, just like in a seesaw.